Thank you to all organizers for the kind invitation. So I will be closing this blog on Lipschitz free spaces by a talk about their biduals, that is continuous functionals on spaces of Lipschitz functions, and in particular their relation to measures. The talk will be based on joint work with Ramon Aliaga from Valencia. So as we already saw in Marek's talk, some of important open questions in the area involve the placement of the Lipschitz free space in its bidual. For instance, deciding for which metric spaces the Lipschitz free spaces are complemented in their biduals, and in particular whether this is true for the space L1. The only known results in this direction so far are the result by Zut, Kalenda, and Kaplitsky, who show complementability of the free space over a finite dimensional Banach space, or a more recent result by Aliaga, Gartland, Petitjean, and Prochaska, who show L-embeddability of the free space over a compact, purely one unrectifiable metric space. Another such question is whether the free space is always an isometrically unique predual of its dual of the space of Lipschitz functions. This question has already been answered in positive for a large group of metric spaces, including all bounded metric spaces or all Banach spaces by Nick Weaver, but in full generality, the question remains open. And then other examples of such questions would be questions regarding weak sequential completeness of Lipschitz free spaces, or involving some weaker forms of weak star continuity of functionals, such as in the case of property X and others. So motivated by these questions, we are now trying to better understand the general structure of the dual of the space of Lipschitz functions, which I will call Lipschitz space. So this Lipschitz space can be viewed in some sense as a metric counterpart of the space of bounded continuous functions over topological spaces, or as the space of essentially bounded measurable functions over a measure space. For instance, Weaver obtains a metric version of Banach-Stone theorem, which says that if two uniformly concave complete metric spaces have linearly isometric Lipschitz spaces, then these metric spaces have to be already by Lipschitz homeomorphic. And the linear isometry comes from this homeomorphism, which is actually a dilation on the metric spaces. In analogy with the measure spaces, we have a Radon-Nikodym type of theorem, which says that the weak star continuous functionals on Lipschitz spaces are precisely order continuous functionals. So therefore, we might also want to compare the functionals on Lipschitz spaces to measures, as those represent functionals on these other two function spaces. And such a description of the dual of the Lipschitz space was actually used in this already mentioned result by Zut, Kalenda, and Kaplitsky about complementability for finite dimensional Banach spaces. So now we will try to study the relationship between functionals and measures for general metric space. So we will say that a functional on Lipschitz space is induced by a measure if its action on a function is given by integrating this function with respect to the given measure. Now I'm being vague about the specification of the measure and the domain, but this is because actually deciding these is the crucial part of the analysis, and we will get to it later. But now, with this intuitive understanding of a measure representation of functionals, we can observe that any finitely supported functional is obviously induced by a linear combination of Dirac measures on the metric space. But not all functionals, not even all weak star continuous functionals on Lipschitz space are induced by measures. To see this, we will borrow a simple example due to Weaver. Let's consider an infinite compact metric space. Then this space has to have some non-isolated point. So let's say it's the base point. Then we can take a sequence of points converging to the base point fast enough so that a functional like here, okay, I don't have a, so hopefully you can see at least a little hand. So that the functional here is well defined, sorry. And now let's suppose that this functional is induced by some finite measure on M. Then if we consider functions as on the picture, the blue functions on the picture with increasing number of the peaks towards the base point, then the integrals of these functions with respect to the supposedly representing measure should be less than the total variation of the measure because they are positive and bounded by 1. But their evaluation at this functional M tends to infinity. So this is a contradiction. So in other words, this functional M here is bounded with respect to the Lipschitz norm of functions, but is not bounded with respect to supremum norm of the functions. So we see that measure-induced elements are weak star dense, measure-induced functionals are weak star dense, but not all functionals are induced by measure. And now to properly compare functionals to measures, we need to decide appropriate measure space on which the measures should be considered. And to do so, we introduce a notion of support for functionals on Lipschitz spaces. So we would want, or we would expect from such support to naturally extend the concept of finitely supported functionals. So in particular, we would want point evaluations to be supported at the considered point. But now if we have a bounded metric space and any compactification of this metric space such that all Lipschitz functions extend continuously, then the evaluation functional at any point of the compactification is a well-defined bounded linear functional on the Lipschitz space. This is because the supremum norm of a function is majorized by its Lipschitz norm. So it is not enough to consider only the metric space M for the setting, but we will want to think of a compactification of the metric space such that all Lipschitz functions extend continuously. At the same time, we would like to achieve some minimality of the support or some uniqueness for the support. In other words, we want zero functionals to have empty support. But if there were 2 points in our compactification, 2 distinct points in our compactification, such that for all Lipschitz functions, the values at these 2 points are the same, which is the case, for example, for Check-Stone compactification, then the zero functional could be represented as a finitely supported functional, and we would get some ambiguity for the support. So what we need from the compactification is that the Lipschitz functions also separate points of this compactification. And this brings us to the smallest compactification of a metric space to which all bounded real-valued Lipschitz functions can be continuously extended. Such a compactification exists. It is called Samuel or uniform compactification, as it comes from a uniformly continuous bounded functions on M. And the compactification has the following crucial properties. One is that any two disjoint closed subsets of the uniform compactification can be separated by open neighborhoods whose intersections with the metric space are at a positive distance. So in particular, they can be separated by Lipschitz functions. And any Lipschitz function can be uniquely extended to a continuous function if we allow values minus and plus infinity. So now, having a proper setting, we can define supports. We would like the support to somehow depict the area on which the action of the functional depends. And this brings us to the following definition. For a functional phi, we define the extended support of phi to be the intersection of all closed subsets of the uniform compactification, such that the functional evaluates as 0 on any function that is 0 on the closed set. So somehow we see these are the sets on which the action of the functional depends. And as we already saw in Marek's lecture, for weak star continuous functionals, we can actually provide a sharper definition of support as the smallest closed subset of the metric space, such that this property is true. So what is important here is that such smallest closed set, the smallest closed set in this class, exists for weak star continuous functionals. This follows from the algebraic properties of Lipschitz spaces. And then for weak star continuous functionals, we get two notions of support. The sharp support, let's say, is the intersection of the extended support with the metric space, and it is dense in the extended support. But we do not always have the existence of such a smallest closed set in this family of functions for a general functional on Lipschitz space. So we cannot really do much better than in this definition. Indeed, to see this, let us have a look at the following example. Let's assume that the base point is not isolated in the metric space. And let's take a sequence of points converging to this base point. Then define functionals as molecules on these points converging to the base point. Then these molecules are uniformly bounded. Therefore, they have some weak star cluster point phi in the dual of the Lipschitz space. And this phi obviously evaluates as 1 on the function which represents the distance from the base point. So what could be a candidate for the smallest set? Well, obviously the action of this functional only depends on values of a function on any ball around the base point. So it should be a subset of any ball around the base point, which could only be the base point itself. But then obviously this condition is not satisfied for the base point because any Lipschitz function is 0 at the base point. But as we said, the function representing the distance from the base point does not evaluate as 0. So really not always does such a smallest closed set, such a smallest set in this family exist for a general functional on Lipschitz space. But what we do get is a little bit weaker version of this localization property, which says that any bounded Lipschitz function is evaluated as 0 by a functional as soon as it vanishes on some neighborhood of the support of the extended support of the functional. And so this in particular means that this property is true for any Lipschitz function if the considered functional is determined by actions on bounded functions. For example, if the support of the functional is bounded, or if it can be approximated by boundedly supported functionals. But this property might really break down for unbounded Lipschitz functions and for functionals which do have some part concentrated at infinity. That is, they cannot be approximated by boundedly supported functionals. So let us see this on an example. Let's consider a subset of R2 as on the picture, the red and blue part, with the inherited metric. And let us define molecules on the red points. Then these molecules again form a uniformly bounded set. So it has a big star cluster point if in the dual of the Lipschitz space. Let's call it phi. Then again, this phi evaluates as 1 at the function representing the distance from the base point. So in particular, it is not a zero functional. But let us see what its extended support is. So if we have any Lipschitz function, which is 0 on the blue part, on the blue points, then since it is Lipschitz, it has to be bounded on the red part. And any bounded function, when we plug it into this functionals mn, then we divide some bounded value by a growing number, so the evaluation tends to 0. So any such function is evaluated as 0 by the functional phi. And obviously, if we have a function which is 0 on the red part, then its evaluation is 0 as well. So what we observed is that the extended support of the functional phi should be a subset of the intersection of the red part and of the blue part. But the intersection of these two is empty. So we got that the extended support of functional phi is empty. In particular, it is a non-zero functional with empty support. So obviously for this one, the property from this localization property does not hold, because again, the function here is, well, any Lipschitz function vanishes on some open neighborhood of an empty set, but this function does not evaluate as 0. And so we see that the property really might fail if we have unbounded functions and functionals concentrated at infinity. Okay, so now that we have the setting decided as the uniform compactification and the notion of support, we can come to the study of the relationship of functionals and measures more rigorously. So let me recall that a functional on Lipschitz space is induced by a Borel measure on the uniform compactification of the metric space if its action on a Lipschitz function is given by integrating the continuous extension of this function to the uniform compactification with respect to the given Borel measure. And these questions in the setting of Lipschitz free spaces were already studied by Ambrosio and Puglisi, who showed that any radon measure on a metric space M with finite first moment induces an element of Lipschitz free space. And it turns out that this result extends to the bidual, namely any Borel measure on the uniform compactification of M with finite first moment induces a functional on a Lipschitz space. This can be seen easily by just majorizing a Lipschitz function by its Lipschitz constant and the distance from the base point. And to pass from this bidual version of the result to the weak star, to the predual version, we really need inner regularity of the measure, or either separability of the metric space or regularity of the measure, so that we can focus only on the support of the measure on which the measure is then concentrated, which is again a separable set. And this then allows us to employ either Bochner integral or Lebesgue-dominated convergence theorem. So this is to show which measures induce functionals. Now let's assume that we have a functional which is induced by an irregular Borel measure on the uniform compactification. What we can say about this functional is that two notions of support of a functional and support of a measure, agree, and that the functional is positive with respect to the pointwise order on the Lipschitz space, if and only if the representing measure is positive. This is because we are considering irregular Borel measures, then we can replace any measurable sets with compact sets and characteristic functions with Lipschitz functions. So this gives us the relation between these relations between functionals and measures. And from the first point here, it follows that such a representing measure has to be unique. And now from the previous slide, or on the previous slide, we saw that if a measure was concentrated on, if this representing measure is concentrated on the metric space, then the functional that we obtain is weak-star continuous, but it turns out that the converse is also true. That is, a measure-induced functional is weak-star continuous if and only if the measure is concentrated on the metric space M. This also justifies the choice of uniform compactification as being compatible in the setting of Lipschitz free spaces. And it can also be seen as an extension of an earlier result due to Weaver, which says that an evaluation of functional at a point of checkstone compactification is weak-star continuous if and only if the point actually belongs to the metric space. The key part for proving both of these results is actually the observation that a point in the remainder of a compactification, whether uniform or stone-Čech, is in a positive distance from every point from the metric space uniformly. So we can separate points in the remainder from the metric space by Lipschitz functions, and even compact subsets of the remainder we can separate from the metric space by Lipschitz functions. But what really allowed us to formulate the result for any functional once we have considered uniform compactification is the fact that in uniform compactification also any two disjoint closed subsets of the remainder can be separated by Lipschitz functions. So this was the key part to pass to any functionals, which we gained thanks to changing the setting to uniform compactification. And so now let us see how to identify functionals which are induced by measures. Again, in the setting of Lipschitz free spaces, a result in this direction was obtained by Ambrosio and Puglisi, who showed that any positive element of Lipschitz free space is induced by a positive sigma finite Borel measure on the metric space. And we get a similar result by dual form, which characterizes all functionals on Lipschitz spaces that admit integral representation as those functionals that can be expressed as a difference of two positive functionals. We will then call them majorizable because they do have positive majoran given by the positive part of the decomposition. So let me maybe explain the statement of this theorem. On one hand, if we have a functional which is represented by a measure, then clearly by considering the positive and the negative part of the measure, we get a decomposition of the functional into a positive and a negative part, or a representation as a difference of two positive functionals. On the other hand, if what we actually prove is a precise analog of Ambrosio-Puglisi result, that is that a positive functional can be represented by a measure. But this measure might have some singularity around the base point, so the difference of two representing measures might no longer be a well-defined measure. Therefore, we don't say really that the resulting functional is induced by the measure, but it has a representation as difference of two integrals. And main step for proving this is to consider functionals which are supported on some annulus around the base point, and to show that such positive functional is a weak star limit of a net of finitely supported functionals with bounded measure norms. It's important that the norms are bounded as measures. Well, then we can find a weak star cluster point of this net in the space of measures, which will give us the representing measure. And then by some limiting procedure, we can pass from annulus to functionals which avoid the base point and avoid the infinity. So this is up to some technicalities. I wasn't very precise in the statement here. It only really holds when we avoid space around the base point and the infinity. And now for such majorizable functionals, in analogy with measures, there exists minimal decomposition into a positive and a negative part, where each of them is represented by a Borel measure, or where they are represented by Borel measures concentrated on disjoint subsets. And we can again, similarly to measures, define a variation of a functional as the sum of the positive and the negative part of the functional. This positive and negative part, they actually come from the Jordan decomposition of the representing measures. And what is interesting is that if the functional is weak star continuous, then this minimal decomposition and the variation are also weak star continuous. So being majorizable for a weak star continuous functional in the Lipschitz free space and in its bidual is the same. So, and we saw at the very beginning that not all functionals are always majorizable, but this is the case, for example, when the metric space is finite. So we might wonder when precisely this happens, when all the functionals on Lipschitz space are majorizable. And for this, it is enough that all elements of the Lipschitz free space are majorizable, which happens exactly when the Lipschitz free space is isomorphic to L1 via an order-preserving isomorphism. And a metric characterization for this fact is that the metric space is uniformly discrete on complements of balls around the base point, where the separation constant grows linearly with the distance from the base point. And this is all I wanted to say. Thank you very much for your attention.
Many thanks, Eva. Okay, do we have any questions from the audience?
Well, I have a question. You mentioned the problem of complementability in the bidual. So capital L1, which is in Lipschitz, isometric to Lipschitz free space, is complemented to in its bidual. So can you recover the proof using your notion of a support for the real line, for example? Does there exist something like sigma additive part of a functional or something like that? Or
Well, we do have a decomposition of, we also introduce a decomposition of functionals by the domains, into parts which are concentrated around the base point, into parts which are limits of functionals on annuli, and into parts at infinity. But no, we have not attempted to recover this proof using the support in the way that you're suggesting. So I'm not sure. We haven't. No, we haven't tried it.
So you don't have a proof of the fact that capital L1 is complemented in its bidual using your notions. Maybe some different one. Maybe. No.
No.
Okay. And one more question.
I don't know. Maybe it is somehow. I mean, we don't have it, but I cannot tell how immediate it would be or not. I'm not sure.
And one more question. You mentioned these measurable elements are weak star dense. Are they also norm dense in the bidual or no?
No, because for example, if you have a compact space with isolated base point, then all majorizable elements in the bidual actually have to be weak star continuous. Okay. But the Lipschitz free space is not norm dense in the bidual. So,
okay. So no other questions. Thank you.
Thank you.
So do I get this right? So if you, let's say, take a how to say it, if I, let's say, fix some probability measure on a metric space, let's say separable metric space, then this weak, well, this norm in f of x actually metrizes the weak convergence of probability measures. Does it have a chance to be true?
Sorry, I'm not sure.
Maybe this is kind of out of the blue question, but well, you can, well, in probability you can consider, let's say, weak convergence of measures and of probability measures, and it looks to me that this is more or less the same. So so that this metric should be more or less giving the same topology or whatever for probability measures, not for all measures.
So you mean the metric on the measures? So the measures viewed as the functionals on Lipschitz spaces, and the measures as the measures. Yeah.
But yeah.
So
it
you
seems
mean
to
the
me
relation of the norms, right?
Yeah.
Right. Actually,
So what weak star topology you consider on the space of measures? Is it like for compact spaces or?
No, well, I want to, let's say, think in terms of probability only. So I have a, let's say, probability measure. So I have the notion of weak convergence of measures, which is actually the weak star convergence. But for in this, when you restrict this to the set of probability measures, then I think this is metrizable. I mean, this fragment of, let's say, the weak star-like topology, and it seems to me that actually this is just metrizable by this metric, but perhaps it should be checked.
So yeah, this I don't know. Now I think I understand better what you mean. Yeah, but I don't know.
Okay.
So using the metric given by the norm on the dual of Lipschitz spaces.
Yeah.
Whether this is the metric, okay, for the weak convergence. Okay, I don't know. That's an interesting question.
Okay. Do you have any other questions? Well, if not, let us thank Eva again. So
thank you.
I'm very happy to have such disciplined speakers, so that there was no, let's say, delay. There were no delays or whatever. So let me conclude this morning session, and we resume in the afternoon. So thank you again for all the speakers of the morning session. Thank you very much. Niels, do you have any other advertisements for now?
Well, I just wanted to check. I was inclined to let the meeting run. I mean, not to actually close the meeting, but just keep it open.